Hi everyone, my name is Vishrant Tripathi and today I'm going to present our work titled Optimizing Age of Information with Correlated Sources. This is joint work with my advisor, Professor Ethan Modiano, and both of us are affiliated with the Lab for Information and Decision Systems at MIT. So let's get started. Okay, so the standard setup in works that typically consider minimization of age of information consists of the following. It consists of n sources that are monitoring some phenomena, and a base station that is interested in receiving updates from all of these sources over some constrained communication channel. And the typical goal in these works is to minimize the weighted sum of age of information across all of these sources. But a key assumption in all of these works is that sources monitor decoupled or independent processes. So when the base station receives an update from source I, it only reduces the age of information of source I. It does not influence the age of information of any other source. But one thing that we might want to consider in more realistic and practical settings is model correlation between sources and the phenomena that they are monitoring. And this is the focus of our work. In our work, we start by proposing a very simple model. This simple model tries to model correlation between sources in a pairwise manner. And the way in which it does this is as follows. So if a node J transmits an update to the base station, we say that it also has common information about another node I with some probability Pji. So if this probability Pji was 1, then node J would always have information about the state at node I as well. Or if it was 0, then they would be completely decoupled and independent. And by tuning this probability, we create correlation across sources. And by specifying probabilities for each pair of sources, we create this correlation matrix that defines the underlying correlation structure across sources. So a bit more detail about our model. The age of information basically evolves in a slightly different manner than standard age of information. So it increases when there's no new information about this particular source I. Whenever the base station receives a new update directly from source I, the age of information drops to 1 because it received new information about the source. But occasionally, the base station receives an update from some other source, say J, which also contains information about node I. And so the age of information of I again drops to 1. So there are two kinds of updates that could cause the age of information of source I to drop to 1. One is updates from itself. The second is correlated updates from other sources. And this happens basically in every time slot based on a Bernoulli random variable with probability Pji. If source J transmits in time slot T, then the base station has information about source J and source I with probability Pji. And the correlation matrix, as I described in the previous slide, which is basically describing all of the pairwise correlations between every pair of source, describes the underlying correlation structure between sources. So this is our proposed model for analyzing correlation while monitoring multiple sources in a wireless setting. Now, what is the underlying motivation behind this model? Why do we care about correlated sources? The answer is real-world applications. There are plenty of examples, such as sensor networks with overlapping fields of view, or sensor networks monitoring some spatial phenomena over a large area where sensors that are close by have similar values that they're measuring, and sensors that are far away have very different values. Vehicular networks where vehicles exchange information locally and then talk to a base station remotely. So vehicles that are close by have common local information, so you don't need to hear from all of them, but just one of them. Another good example is federated learning, where if users have very similar data sets, then the gradient updates that they send to the central server would be very correlated. And this is something that is not typically captured. People assume that users have diversity in their data sets, but that's not necessarily true. And we want to capture all these different kinds of settings using our model and then try to optimize age of information in it. So that's our next slide. Okay, so given this correlation model, the goal of our paper is to optimize the weighted sum of age of information. Just as prior works, we optimize weighted sum of age of information, but under this correlation model. Now, this basically raises 5 interesting questions, and we answer all of these questions to some degree through our paper. The first question is, can we design a scheduling policy that can actually take this correlation matrix P into account? The second question is, now that we have designed a policy, does it actually help? So does it actually help to take correlation into account, or do you get the benefit of AOI reduction for free without designing a policy that thinks about correlation? The third question that we want to answer is performance guarantees for the policies that we develop, and providing scaling results depending on uh, the correlation matrix. How does the scaling over the network change? How much can correlation help? Intuitive understanding of this AOI reduction. The fourth question is, can we generalize to a larger class of correlation models? So the correlation model that we started with was this very simple Bernoulli pairwise correlation. Can we possibly generalize to a slightly larger class of models? And the final question is, what if we don't know the correlation matrix in advance, as is typically true in most practical settings? And what if this correlation matrix in itself is time varying? Can we design a policy that gradually adapts to this correlation between the sources over time? And we will answer the first four questions with analysis. And the fifth question we will answer partially using numerical results. Okay. So to design a scheduling policy to solve this problem, we start with the class of stationary randomized policies. Stationary randomized policies are essentially policies in which at any given time, source I is scheduled with some fixed probability pi I. So the entire policy can be described by just one probability distribution over the set of sources. We show that finding the optimal stationary randomized policy that minimizes the weighted sum correlated age of information is equivalent to solving the following convex program. The details for this convex program are not really relevant. The most interesting part is that it is convex, so it can be solved very efficiently. And the fact that the solution that we obtain has a nice performance guarantee. So we show that the optimal stationary randomized policy is only a factor of 2 away from optimal. Next, we will try to incorporate Lyapunov drift style policies to design a max weight scheduling policy. To do this, we basically use the solution of the stationary randomized convex problem, find the optimal stationary randomized policy pi SR. Using the parameters of pi SR, we construct a linear Lyapunov function. The exact details of how we construct the Lyapunov function is given in the paper. I avoid going over those details right now due to time constraints. But the key idea of the Lyapunov max weight policy is that it minimizes Lyapunov drift across every time slot. So at the beginning of every time slot, it computes the Lyapunov drift for every possible scheduling decision that it can take, and then chooses the decision that minimizes the Lyapunov drift. Intuitively, what it's really doing is it's calculating the benefit of scheduling source I. So this is just the benefit that you get from scheduling source I, because age of I will reduce guaranteed, because the base station will receive a new update from source I transmits. But then in expectation, I will also have some common information about other sources J with some probability Pij. And so age of other sources will also drop in expectation with some probability Pij. So it basically tries to calculate this combined weighted sum of the total benefit of scheduling a particular source, and then schedules the source which has the highest weighted sum. This is a slightly more complicated policy. What we end up showing is that the max weight policy is also at most a factor of 2 away from optimal. So it has the same theoretical guarantee as the stationary randomized policy. When we simulate it, it turns out that the max weight policy actually performs much better than the stationary randomized policy. And in fact, almost comes close to a lower bound that we derive in our work in detail. Yeah, so the need for the max weight policy is basically to beat stationary randomized policies. Stationary randomized policies are nice to analyze, and they give us a way to prove analytical results. But then when we go into practice, we need something that works better, and that's where the max weight policy comes in. So now that we have designed a scheduling policy that can take correlation into account, and for which we have performance guarantees, so we know that it works well, can we talk about how correlation improves age of information or reduces age of information? So suppose that you had the best policy given a particular correlation matrix and the weights for the age of information. How much reduction in average age of information can you get? So to analyze this setting, we focus primarily, to analyze scaling, we focus primarily on the symmetric weight setting. And in the symmetric weight setting, basically the weight for every source is 1 over n for n sources. And so the first thing that we need to do to analyze scaling is to create something called a correlation graph. The correlation graph connects source I and source j if they are correlated by some probability Pij, which is higher than some threshold P. So we set a threshold P. This is the minimum level of correlation that we will consider. Anything lower than that, we will ignore. And for every pair of sources which has correlation higher than this threshold P, we create an edge in this graph G. So now that we have this graph G, we compute something called N cover. N cover is basically the size of the smallest vertex cover set on G. A vertex cover set is basically a subset of nodes such that for every node in the graph, there exists some node in this vertex cover set such that there exists an edge between the original node and the node in the vertex cover. So a vertex cover is basically a small subset of nodes in the graph that can cover the entire graph. And what we do is we show that under the best possible, even under the best possible policy, the weighted sum average age of information has an upper bound that can basically be derived using the two quantities N cover and P. It's basically N cover divided by P. And this is an important scaling result. We discuss in our paper how we can apply it to things like random geometric graphs or scale-free graphs. And we can think about or reason about basically how close or how far these sensors are, or how the degree of correlation influences the improvement in AOI. But scaling also gives us something else. And through scaling, we derive another interesting result. This result is basically answering the question, is using correlation actually helpful? So more specifically, the question is, can we get the benefit of AOI reduction via correlation for free? Suppose I run the usual max weight algorithm that has no idea that these sources are correlated, but then it uses the actual correlated age of information to run. So it does not use age of information that is uncorrelated. Then we would still get the correlated updates from other sources. So do we actually need to incorporate the idea of correlation itself into our scheduling optimization? The answer is yes. What we show is, using the scaling result, that there exists some correlation matrix P such that the gap of performance between the uncorrelated max weight policy and the correlated max weight policy can grow as quickly as the size of the network. So it can grow as quickly as big omega of n. And so a max weight policy that ignores the correlation matrix P can perform much worse than one that uses P. And the intuition behind this result is kind of simple. So think of just one node and think of it as being correlated by very small amounts to every other node in the network. Then one policy is to just schedule this node always and never listen to every other node. Another policy is to do round robin across all of these nodes. It turns out that the performance gap between these two policies can grow linearly in n, depending on what the correlation parameter is. And that's how we show this result. So basically, if you have a set of sources which has a very small cover set, so basically a very large number of sources which are monitoring a very low dimensional phenomena, so they can be described by a very small number of sources or sensors, then it is sufficient to just monitor those small subset of sensors and not perform scheduling by asking for updates from every source in the network. And this is how we get the improved performance in AOI. And this has some relations to subset selection problems in control and wireless literature as well. Another thing that we show in our paper is this notion of robustness. So till now, all of our results were for the simplistic Bernoulli model of correlation, where if node J transmits to the base station, then it has common information about node I with some fixed probability Pji, and this is modeled using a Bernoulli random variable IID across time. But instead, suppose we have age of information evolution for I as AI of t plus 1 is some 1 minus xji of t, where xji of t captures this correlation between source j and source I, times AI of t plus 1. So if xji of t was 0 always, then this would be the usual age of information evolution, where it just increases by 1. If xjift was always 1, then age of information of I would always be 1. So j is basically identical to I. And the interesting part comes where xji of t is something between 0 and strictly between 0 and 1. In our original model, we assume that xji of t is a Bernoulli random variable with probability pji. Now, instead, in our robustness results, what we assume is that xji of t is a general random variable, still IID, but all we ask of this general random variable is that it remains between 0 and 1, and it has an expectation that is pji. So instead of asking for binary correlation, 0 or 1, where you get a full update about another source when you get a correlated update, now we can get partially correlated updates between sources. And in this larger class of models, where instead of full correlation or zero correlation, averaging over time, we get these partially correlated sources, we show that given any stationary randomized policy and a correlation matrix P, all such classes of models have the same age of information. So it is sufficient to analyze the binary model to get results for these partial correlation models as well. And that's why our model is general. And because the binary correlation model is easier to analyze for policies that are not stationary randomized, that's why we focus on this binary correlation model. And that's why it gives us such nice and interesting results, both in terms of scaling, in terms of deriving performance bounds for the max weight policy, and in terms of figuring out how to design an online policy as well. So now that we have covered all of our theoretical results, we will briefly discuss some of our numerical results as well. The first set of numerical results is basically comparing different classes of policies over random geometric graphs. So what this means is we choose n sources, we place them randomly on the unit square in 2D, and then we connect sources that are very close to each other with some probability. And we say that what we have created is a random geometric graph, which basically represents the correlation structure of these sources. So if sources are close by, then they're correlated. And then if sources are far apart, then they're not correlated. And under this kind of random creation of correlation structure, as the network size increases, we see that our proposed policies, which are basically the max weight correlated policy and the optimal stationary randomized correlated policy, perform better than the standard stationary randomized policy, and then the standard max weight policy, which in this case would be something like max age of information first. So what we see is that even for a setting which looks fairly symmetric, because we have assumed that all sources look identical on average, if averaged over multiple instances, we see that even in this kind of a setting, there is significant performance improvement if we consider correlation. And we see that there's roughly 33% performance improvement by using correlation in max weight compared to not using correlation in max weight. The second setting we consider is scale-free random graphs. So the first setting that we consider, random geometric graphs to model correlation, this is a good way to model sensors monitoring some spatially correlated phenomena, because sensors close by are correlated, but sensors far away are not correlated. The second model, which is scale-free random graphs, is about networks that often appear in the real world. So there has been this long line of work starting by Barabashi and other people working on scale-free random graphs, where they have shown that things like social networks or various other influence models basically have this preferential attachment scheme that ultimately creates scale-free graphs. So what we do in this setting is, for any network size, n, we basically create a random scale-free graph that describes the underlying correlation structure between these sources, and then run our policies. Now, what's interesting about scale-free random graphs here is that they have very low vertex cover numbers, which means using our result from earlier, which showed that the scaling of age of information depends on the vertex cover, and because these graphs have small vertex covers, we see that there's a significant performance improvement between policies that ignore correlation and policies that consider correlation. So basically, as n increases, policies that consider correlation have roughly constant AOI. So AOI does not even increase with the size of the network. While for policies that ignore correlation, such as max AOI first, the age of information increases as the size of the network increases. So a significant performance difference. Now, an interesting application of this idea would be basically federated learning, where we can think of the data sets that different users have in a practical context, depending on, for example, a social network context. It is easy to imagine that the underlying correlation between their gradients might be arranged in some sort of a scale-free graph. And so this can have important implications if you're trying to sample users so as to maximize the diversity in the gradients that you are trying to obtain for your federated learning scheme. And finally, as I had promised, we want to consider the case when the correlation matrix is unknown and when it is time varying. The key idea in this setting, which we explore in our paper in a bit more detail, is to design an online max weight algorithm that can learn this correlation matrix P using exponential moving averages and still be computationally efficient. And that's what we basically do. We don't provide regret analysis results, but what we show through numerical simulations is basically that our exponential moving average max weight policy performs almost as well as the Oracle max weight policy that basically knows the correlation matrix in every time slot. And it performs much better than the naive policy, which is basically max age of information first. So it does not know the age of information correlation matrix at any given time slot. So basically, you can incorporate the learning of the correlation matrix in an online manner in the max weight scheduling policy. And this leads us to our future work. So basically, there are 3 important lines of work that we are considering. The first one is to extend our approach to general nonlinear age of information costs. So in age of information literature, there has been basically this trend to go from, we start with weighted sums of age of information, then we go to general nonlinear age of information costs, and we can do the same thing for correlated age of information as well. The tricky part is trying to develop a correlated restless multi-banded framework and then basically solving it using something like correlated Whittle index. And we are still trying to figure out the exact details for this. The second direction of extensions is basically regret analysis for the exponential moving average max weight, as I discussed in the last slide. And then the third, and perhaps the most interesting direction, is applying this kind of intuition that we gain from our simple model regarding monitoring of correlated sources for freshness to applications in robotics and federated learning, and see if we can get some gain in performance in real systems. And that basically concludes our talk. Thank you, and feel free to send any questions to me at this email ID. Thanks a lot.